I'm here to talk with you about the difference between global and local coordinate systems. Because as you go on to more complex problems, you will find that this distinction becomes helpful, and sometimes it's more useful to use global coordinate systems, and sometimes it's more useful to use local coordinate systems. Now, normally, you've seen problems like this before, where you have like a projectile, has an initial velocity and launch angle, it launches up and then hits the ground later. You know that you create coordinate systems for this as part of solving your problem. You could create a coordinate system here if you want, or if you want, you could create a coordinate system where the origin is at the part where the particle is first launched. And you know that it doesn't matter where you place your coordinate system, you'll get the same answer. In fact, you could do really weird coordinate systems. Like you could do something like this if you wanted. You could change signs as well so that the downward direction and to the left is positive. It doesn't matter. But in all cases so far, you have largely been using a global coordinate system. So what do I mean by a global coordinate system? By a global coordinate system, I mean a coordinate system where you have just one coordinate system for the entirety of your problem. So the entirety of the motion of your object, the entirety of the problem. Whereas by a local coordinate system, I mean a coordinate system that exists at just one point of your problem. In fact, you could place a coordinate system wherever you wanted. You could place one here, you could place one here. You could have so many coordinate systems if you wanted. At each point of the problem, at each point of the motion, you could have another coordinate system. So what a local coordinate system ends up meaning is that you have multiple coordinate systems in the problem. And so, for example, you might have a coordinate system for one part of your object's motion and another coordinate system for another part of your object's motion. So let's make an example of that with this problem. It's a bit of a silly example. You wouldn't want to do it for reasons I'll discuss in a moment, but you could make one coordinate system here for this part of the motion of your problem, and then you could choose another coordinate system up here. So one coordinate system for the motion of your object until it reaches its maximum height, and then another coordinate system for when it reaches its maximum height and until it reaches the ground. Now, when choosing your local coordinate systems, there are some considerations to make. One consideration is it's often better to keep the directions the same. So for an example, my up direction is positive in both coordinate systems and to the right is positive in both coordinate systems. It's not always possible to do, especially if you have rotated coordinate systems, but that's often a useful thing to do. But all right, let's see what we can do with this. When you have local coordinate systems, the things you need to do is you need to tie them together somehow. So for an example, in my red coordinate system, I could find my X and Y positions as I go to the top. And if I wanted to, I could figure out what my height was, my delta Y, which I'll call little h, as I go from here all the way to the top. I could figure out what my final velocity was in the x, and in the y direction, I know it's 0 because it's the maximum height. Using that my final velocity in the y direction is 0, I can actually use this and a kinematics equation to find the maximum height of the particle, this h, this delta y that it travels. Well then, for the next part of my motion, I'm in my blue coordinate system, and I can have position of time, I can have a y function of time for x and y coordinates. I can have a v initial in the x direction and a v initial in the y direction, but then here is how you will tie the coordinate systems together. Your initial velocity in the blue coordinate system is the same as your final velocity in the red coordinate system. So you're going to have a velocity in your red coordinate system when you're at the top that looks something like this, right? This is your v final in the red coordinate system. There is no y component, there is only x component. And then in my blue coordinate system, if I'm looking at this velocity vector in the blue coordinate system, I see that this is my initial velocity for this part of the problem. And in my blue coordinate system, then my initial velocity in the x direction is equal to my final velocity in the x direction in the red coordinate system. And likewise, my initial velocity in the y direction, there is no y direction in the blue coordinate system as well. So my initial velocity in the y direction is still my final velocity in the y direction in the red coordinate system. Then, although my initial positions are 0 in the blue coordinate system, even as they were in the red coordinate system, because in both cases I placed my origin at the initial position of the motion from when I start keeping track of the motion, I can use this h right here that I solved for, earlier in the blue part of the problem to figure out whatever I want in the next part. So I know that the distance from here to here is little h plus big H. And I know what little h is because I solved for it in the red part of the problem. So that's how you use these coordinate systems. You create coordinate systems for different parts of your problem, and then you tie them together by using final quantities that you solve for in one part of the problem as initial quantities in the other part, and use whatever shifts that you get in the x and y direction to figure out final and initial positions in the other coordinate system, and so forth. Now, doing this for this problem is a bit silly. It's a lot better to use a global coordinate system. When do you want to use a global or a local coordinate system? Well, it turns out that so long as you don't have a part of the problem where you have a rotated coordinate system, or so long as you don't have a number of objects moving in different ways, so a more complex system, it's often better to use a global coordinate system. Local coordinate systems are useful, but as you can see, it required having two different sets of equations for the different parts of the motion. If you just want to have one equation for the entirety of the motion for each of your objects, then it makes more sense to use a global coordinate system. And yes, it's possible that your object could change acceleration, and so it's a two-part problem, but you'll still have fewer equations to deal with generally if you use a global coordinate system instead of a local coordinate system, if you just have one origin for your problem instead of multiple origins at different parts or places of motion in your problem. So those are global and local coordinates, and a simple example of using them and where they are useful and where they are